The next family of functions is the family of rational functions. So these guys aren't quite as friendly as the polynomial functions. These guys are actually fractions, where I actually have a quotient of polynomials. In other words, I have a polynomial in the numerator and a polynomial in the denominator. So let's see if we can come up with some ideas as far as graphing these. So starting out with number 1 here, I'm thinking, well, this is a pretty simple rational function. Let me say even one other thing, which is, well, what if I think for a second about what if I had something even simpler? Just think about something like this for a second. Well, if I had something like that, I could actually graph that by transformations. Why? Because, well, the base graph would be the reciprocal function. I'm not doing a detailed graph for this one. I'm kind of just illustrating something, and then I'm going to go back to the other problem. Then I would say, okay, my next step would be that shift left 1. Okay, and then I would move everything, what, down to? Okay, so just a rough sketch. So I could get the graph of that function really quickly via transformations. The thing about it is, well, with the problem I'm doing up here, I can't actually see the transformations because I have that x in the numerator. So what I'm going to have to do if I want to do this problem by transformations is I'm actually going to have to put this into transformation form. So that'd be kind of option 1. Okay, so how would I do that? Well, I would actually have to compute the long division. So good thing we did a little review on dividing polynomials. So now I remember how to do long division. I don't like how I did that. I wanted to put this with this. Okay, because I'm really going back to the earlier example. So I'm saying, well, how can I graph that? Well, the issue is I have the x in the numerator. So what will I do? I will have to put this into transformation form, and I'll have to do that by doing the long division. Okay. So let's go ahead and set that up. So this will be an easy long division. So let's see, 3x plus 6, e1. Okay, so that means that 3x plus 7 over x plus 2 is 3 plus the remainder is 1. That stays over the x plus 2. So here that guy is written then in transformation form. So then I can go ahead and graph this. So my step 1 would be the base graph, which is 1 over x. So let's see. It's that reciprocal function. It's one of our library functions. So let's see, if I plug 1 in there, I get 1. Put 2 in there, I get a half. Put a half in there, I get 2. Okay, this function's symmetric over the origin. It's an odd function. So I'd have the same points, but negated in quadrant 3. Okay, so there's the graph. This guy has a horizontal asymptote. Y equals 0. It has a vertical asymptote. X equals 0. Okay. Then I go ahead and go on with my transformations. So now I'm going to shift left 2. Vertical asymptote is going to shift with the graph. It's going to be at x is -2. Horizontal asymptote will slide, but will still be at y equals 0. And I'll move my points. So then I'll have 0, a half. I'll have, let's see, -1, 1. I'll have -1.5, 2. Okay, and then, let's see, -1, -1 is going to be at -3, -1. And then my last step, so the last step is accounting for that +3. So that's going to be moving the graph up 3. Okay, so I'm looking at the previous step. I'm going to move everything up 3. So 0, a half. Let's see, actually I think I'll put my asymptotes on here first. I think that's a good idea. So vertical asymptote stays. Horizontal asymptote shifts up 3. 0, 3.5. -1, 4. -3/2, 5. Okay, and then let's see, -3, 2. All right, and then I have the final graph of my function. So that's option 1 for how I go about graphing this function. Okay, option 1. So what did I do? Well, I had to put that in transformation form by long dividing. Then I had to go through these 1, 2, 3 steps where I carefully move all the points around. I end up with this nice, complete final graph, but that was long, was a lot of work. So what is in option 2 then? So I do have another option. So And I'm going to say option 2. So starting out with that same original function, instead of putting it in transformation form, what I'm going to do is I'm going to gather information. Okay, so I don't even have to do the long division. Instead, I'm going to say, okay, well, what kind of information can I come up with? Like, what are some things we could find? We could find the y-intercept. Let's see, if I plug in 0, I'd have, what, 7/2? What about the x-intercepts? So I set the whole function to 0, but then when I clear the fraction, aren't I really just setting the numerator to 0? So if I have just one fraction, I can really use a shortcut to find the x-intercepts, and I could set the numerator to 0. Here's the x-intercept. Okay, let me see if I can figure out the asymptotes. So what are vertical asymptotes? Well, vertical asymptotes, if you look back at the graph here, vertical asymptotes are x values where the function is undefined. In other words, they're values of x where the denominator is equal to 0. So when I'm thinking about vertical asymptotes, I'm thinking about where is the denominator equal to 0, because I'm asking where is the function undefined. So if I look at my function here, I can tell you immediately the vertical asymptote for this guy is going to be x equals -2. By the way, I'll just make a comment about asymptotes here while we're kind of defining them. So vertical asymptotes occur where the denominator is 0. This is where the function is undefined. So I can never divide by 0. So a vertical asymptote is never crossed. Okay? But now we're going to think about the other type of asymptote, or one of the other types at least. What about horizontal asymptotes? So look back at this graph, because I'm kind of thinking, well, what do horizontal asymptotes tell me? You see how it's only on the ends of the graph that the function actually gets close to its horizontal asymptote, right? It's on the ends, the far left and the far right. Okay, so what is the horizontal asymptote telling me? It's telling me what happens on the ends. Okay, so think about end behavior. Remember, on the ends, what's going to dominate is going to be the leading terms. Okay? Just like when we were just looking at polynomials. So if you look back at this function, the leading terms, top and bottom, are 3x and x. So the horizontal asymptote for this guy is going to be 3. Okay? Now, I just wanted to comment that generally speaking, a horizontal asymptote, because that tells us only what happens on the ends of the graph, a horizontal asymptote is actually sometimes crossed. Okay? So we're going to get to some examples a little bit later where that actually occurs. In this case, the horizontal asymptote is not crossed because this is a translation of a reciprocal function. Okay? But we'll get to some other examples. a little bit later. Let me see how I want to do this. I kind of want to, well, let me just move this down. I was just thinking, well, let's see if we could graph this using the information, if there's room here. I guess there is, using the information that we found. So here's the graph we came up with earlier via transformations. So I'm just thinking, well, what if instead we try to take all this information we found and come up with a sketch of a graph that way. So let's see, we found y-intercept is 0, 1, 2, 3.5. We found the x-intercept is -2 1/3. 0. Found the vertical asymptote. X is -2. Horizontal asymptote is y is 3. So using the information that I found, that's actually all I would have on the graph. Okay, so with these, sometimes what I have to do is I have to actually get an additional point or so by actually taking a value of x and actually plugging it into the function. So I don't know, what if I plugged in like -1? Just pick something. So let's see, that'd be -3 plus 7 is 4 over -1 plus 2. Okay, then I'd have an additional point. And so I'd have 3 points on the graph, and there would be my shape. Okay, so what do you think? Looks like I got the same graph, right, via transformations or via putting together information. Now, second option here is typically a little bit faster, but then I often have to go back, get an additional point or so by plugging values in the function. Oh, should we do one more thing with this one? We're to squeeze this in. Let's do the domain and range. In case looking at either of those final graphs, the domain is going to be all the x's where x is not -2. The range is going to be all the y's where y is not 3. Okay, not too bad. Okay, let's go on to next example. This one. Try to move that up more. Okay. So we'll use option number 2. So we're going to try to put together information. So we'll start out with, say, the y-intercept. So I set x to 0. Okay, so this doesn't have to be to scale, but I'll label. Okay. For the x-intercepts, remember I used that trick. I set the top equal to 0. So I actually can read that off, right? Okay. What about the vertical asymptotes? Remember, for those, I look at where's the denominator equal to 0. So let's go ahead and factor this. What is that? +3 and -4? So my vertical asymptotes would be -3 and 4. So notice something with my notation. You see how when I'm writing a vertical asymptote, I'm writing that as x equals a number. These are lines. Okay, versus when I write intercepts, I write coordinate pairs. These are points, right? So it would not be appropriate to write an asymptote, say, as a point. It's not a point, it's a line. It's just something to notice with the notation. Okay, so let me put the asymptotes on the graph. Now let me get the horizontal asymptote. So remember, for that, I'm thinking what happens on the ends. I'm looking at the lead terms. Okay, so when I go back up here, here are my lead terms. So what happens there? So on the ends, my graph is going to look like x over x squared. That's like 1 over x. So then I have to say what happens to 1 over x as x gets really big, as x goes to positive or negative infinity. Well, as x gets really big, I have 1 over 100, 1 over 1,000, 1 over 10,000. This goes to 0, right? So my horizontal asymptote is actually y equals 0. So actually, anytime I have a higher power in the bottom, a higher degree in the bottom than I do in the top. I have degree 2 in the bottom, degree 1 in the top. I could tell you immediately my horizontal asymptote is going to be y equals 0. That's actually the simplest case because the bottom of the fraction is going to be a lot larger than the top. Okay, so let me try to dash that in. Okay, so that's the information I have. So look at this. Here's something kind of interesting. The horizontal asymptote is y equals 0. So here's an example where the graph actually crosses its horizontal asymptote, crosses at that x-intercept of -1. Okay, so what can I do next? So let's see, how many regions does my graph have? So actually the number of regions is determined by the vertical asymptote. So I have to fill in something over there, something here, and something here. Okay, 3 regions, 1, 2, 3. Now it happens that the points that I have, the intercepts, all fall in the middle. But I still have to fill in all the regions. Now, I mean, I guess I could go back here and I could start plugging in points, but I think I could be a little more clever and I could actually probably graph this just with the information I have. Look at this. I mean, I have to connect these 2 points. Look at the x-intercept of -1. You see how it has a multiplicity of 1? That means the graph crosses at that x-intercept. If I zoom in really close there, I see a line. So I have to have something like that. I can't cross the vertical asymptote. Now I couldn't come back up through here because if I did, I'd have another x-intercept, which I do not. Okay, so the graph has to come down. I don't know what it does in here. Maybe it does something fancy like that. I don't care. You'll look more at that in calculus. For us, we're going to say we know it comes down. Can't cross that vertical asymptote. Okay, now I could plug in points on either side, or I could do this. I could say actually the vertical asymptotes have multiplicities as well. The multiplicities of those are both 1s. They have odd powers. Now, the interpretation of multiplicities of asymptotes is a little different than the interpretation for multiplicities of zeros, although it's similar. So if I have an odd power, and I think, okay, so that generally tells me, well, if I have an odd power, something crosses, right? So it changes sign from negative to positive, okay? So that's the interpretation when I'm thinking about vertical asymptotes and their multiplicities. I'm thinking, if I have an odd power, what's going to happen is my graph is going to change sign as I cross that asymptote. So look, as I go across x equals -3, see how to the right of -3 I'm above, my graph is positive? That means to the left, I have to be below. Has to be the opposite sign. Okay, so that gives me enough information. Has to look like that. Has to approach the horizontal asymptote on the end. Can't cross the vertical asymptote. Okay, same idea at x equals 4. See how the multiplicity is 1? So I'm below here. I have to be above over here. Change sign. Okay, so that's kind of cool. That actually makes it really easy to actually come up with that fairly complicated graph. All right, so there's my graph. We do one more thing with it. How about let's list the domain. And this one looks like I can even get the range. Looks like all real numbers. Okay, let's do another one. Okay, this guy's already factored. Look at that. Let's get the y-intercept. To get the x-intercepts, I look at the numerator, the top equal to 0. I can actually read those off. Vertical asymptotes, I look at the denominator. Denominator equals 0. Stash those in. Horizontal asymptote. Now I look at the degrees. Now the thing with this one is the degree of the numerator is actually x squared. Degree of the denominator, or rather the degree of the numerator is 2. The leading term is x squared. The degree of the denominator is also 2. The leading term of the denominator is also x squared. So actually, if I divide the leading terms, my horizontal asymptote is y equals 1. So remember how we said sometimes functions cross the horizontal asymptote? So seems like a valid question then. Does the graph cross its horizontal asymptote, y equals 1? So if you look back up here, see how in this last example I didn't have to answer that question separately. That's because the horizontal asymptote was y equals 0. So I already knew that graph crossed its horizontal asymptote at the x-intercept of -1. But down here, when I put that horizontal asymptote on the graph, I mean, I don't know if the graph crosses or not, because in this case, the x-intercepts have nothing to do with the horizontal asymptote. So I have to answer this question separately then. Okay, so how am I going to do that? I have to say, is the function, so where's the function? X times x plus 3 over x minus 3, x plus 2. Is that function ever equal to the value 1? In other words, is the y ever equal to 1? So what I'm doing here, in general, is I'm setting the r of x equal to the horizontal asymptote. Okay, and then I have to solve. So let's clear the fraction. So it's 1 times x minus 3x plus 2. Combine like terms. See, add x. So I do get an x value. So yes, the graph does cross its horizontal asymptote at -3/2, 1. So we'll do one later where the graph doesn't cross, but what would happen is you would get a statement here that was false, like 4 equals -6, like all the x's would cancel. Then I would have no solutions. In that case, I would say the graph does not cross. We'll get to one like that later. Okay, but yes, at -1.5, 1, the graph does cross its horizontal asymptote. All right, so then let's see if we can fill this guy in. All right, so everything has a multiplicity of 1. So at the x-intercept, graph crosses. If I zoom in close, I see a line. So that means if I connect these 2 points, I have to cross that intercept at 0. Okay, that means if I was to zoom in really close here, I'd basically just see a line. Seems okay. What else do I know? I know at -3, the graph crosses like a line. So if I zoom in close there, I see a line. Okay. Now look at the asymptotes. X equals -2 has a power 1. That means as I move across that vertical asymptote at -2, I change sign. But look, I'm below here, I'm above here. So that matches up. Look, 3 also has an odd power. So as I go across x equals 3, I have to alternate sign. So I'd have to be above. And so there's my nice final graph with actually not that much work. It's pretty cool. Okay, what else is there? do another one. Okay. So when I set the top to 0, maybe I should go ahead and finish the factoring here. Okay, this one only has one vertical asymptote if I look at the denominator. So that means I'm only going to have to fill in two regions. I have this region, and then I have this region. Okay, so this graph's maybe a little simpler. So the only thing about this one that's a little more interesting is when I go to look now at the horizontal asymptote. I look at the degrees, right? I look at the lead terms. So if I divide the lead terms here, I have x squared over x. Well, that leaves me with an x. Something like a y equals x is actually not a horizontal line anymore. So actually what I have in this case, when I have a higher power in the numerator, is I actually no longer have a horizontal asymptote, I have a slanted asymptote. So in order to find the equation of that slanted asymptote, what I actually have to do is, again, I have to do a long division. Okay? It's an easy one again, but nonetheless, let's see, it'll be x, 3x plus 3, 3x minus 3, the remainder is 3. Okay, so what is the slanted asymptote? Well, the slanted asymptote is actually y equals x plus 3. So why is it that, so slanted asymptote, there's that. I was just curious, why is it in this context that the remainder doesn't matter? Because if I actually wrote out the long division, here's what it would look like. But the thing is this, the slanted asymptote, remember, tells me what happens on the ends of the graph. So x is a very large number in magnitude. If x is a big number, this fraction goes to 0, right? That's 3 over a huge number. So actually the remainder is irrelevant in terms of the slanted asymptote. I just need to know the quotient. So the slanted asymptote is just y equals x plus 3. So in this context, I don't care about the remainder. Okay, let me graph that. So the y-intercept is 3, the slope is 1. There's that. There's that vertical. Okay. All right. So then we need to check, would it be possible that the slant asymptote could be crossed? Well, if I set that equation up, what am I looking at? I'd have x squared plus 2x over x minus 1. And I'm saying, is that ever equal to x plus 3? Well, look what happens. In this case, look at the line I get. Remember how I was saying you'd get a false statement? So no, the graph does not cross. There are no solutions to that equation. Okay, so remember, now I need to fill in. Remember, there are only two regions. Something happens here, and something happens here. Okay, let me tell you something that students like to try to do with these problems. They like to say, oh, well, on the left, I'm going to put like something here and then something here. Well, that would not be possible because then this would not pass the vertical line test, right? It would not be a function. So that can't be the case. Okay, so something here and something here. That's it. So let me see. Let me look up here at my multiplicities. Powers of 1 on the x-intercepts. Okay, so it has to be cross, cross. Now look at the vertical asymptote. Power 1, change sign. So if it's below here, it has to be above here. Okay, well that makes sense. Couldn't be below. Because if it were below here, then it would actually have to have another x-intercept, which it doesn't. Okay, so everything matches up. The domain everything but 1. For this one, I actually couldn't give you the range. That's kind of interesting. I could say minus infinity to something, union something to something, right? But without calculus, I can't tell you how high and how low the peak and the valley are there. Okay, so actually I couldn't ask you the range for this one. And one more. So lots of different cases to look at. This is the last one. Let me start this one out a little differently. Let me start this one by saying, what's the domain? Okay, let me see. That'd be everything but -2, -1, and 2. All right. Now, let me go ahead and finish factoring this. Look at this. So something different happens this time. Something that hasn't happened yet. I actually cancel a factor. So actually, I'll move this. My reduced fraction looks like this. So this is my reduced fraction. So I'm going to use this reduced fraction to go through the rest of the calculations. Let's see what happens. So if I plug 0 in there, I get 0 times 4 over -2 times 1, I get 0, right? X-intercepts. Remember, I'm looking at the reduced fraction, looking at the numerator. What are the x-intercepts? -4, 0, 0, 0. Okay. The vertical asymptotes. Looking at the denominator of the reduced fraction. The vertical asymptotes would be -1 and 2. Okay. Horizontal asymptote. To look at the leading term. So let's see, I'd have an x cubed over an x to the 4th. So that's going to be y equals 0, right? I have a higher power in the denominator. So this is the easy case with the horizontal asymptote. Okay, so what have I not accounted for? You see how back up here that x plus 2 factor canceled? So x equals -2 is not in the domain, but it's not a vertical asymptote. So what is it? It's actually a hole in the graph. Okay, so if a factor cancels, that actually means I have a hole in the graph where x is -2. Okay, so let's do it this way. Let's say factor cancels, hole at x equals -2. So let's go ahead and finish graphing. Then we'll go back at the end and we'll say we know whenever a factor cancels, there's going to be a hole in the graph at that x value, okay? But let me go ahead and complete the graph just using the reduced fraction, then we'll account for that hole at the end. All right, so let's see, how many pieces does my graph have? It has 1, 2, 3. Okay. So I've got to fill in all 3 pieces. Now this one, I don't think I have enough information. I think I would need 1 more point. And then I bet you I could fill in the graph. Okay, so let me pick something. I don't know, I'll pick a number like 1. Let me plug 1 in that reduced fraction. So what would that be? -1 times 8. So I don't care the value so much as I care if it's negative or positive. Because I bet you with that information, knowing that at 1 the function is negative, I could now complete my graph. Okay, because now I can use the multiplicities. So let's see. The multiplicity of x equals 0 is 2. That means the graph touches at x equals 0. That's interesting. So I must have something like this then. Okay. Well, let's look at what happens as I cross those vertical asymptotes. Well, both of those powers are odd. So again, that means I'm going to change sign. So see how I'm below here? I'd have to be above here. I'm below here, I have to be above here. Opposite sign. So it'd be like, have to connect that with, I'm trying to draw that a little bit nicer. Okay, what happens at -4? Well, multiplicity is 1. Crosses. Looks like a line. Okay, so if I was to zoom in really close here, I would see a line. Okay? However, be careful. So does this go down like that? No, it cannot, because remember on the ends, the graph must approach its horizontal asymptote. So it does not dip down like that. Yes, it crosses. Without calculus, I don't know how far this dips down. Okay, but it comes up towards the horizontal asymptote on the end. I do know that much. Now there are no other x-intercepts on the right. Graph would have to look something like that. Oh, so then what have we not accounted for? The last thing, what about this hole? I'll put it here, I guess. The hole at -2, comma. So I have to look at the reduced fraction. I have to evaluate at -2. So what is that? It's going to be -2 squared. -2 plus 4 is 2. -2 minus 2. -2 plus 1 is -1 cubed. What is that, 2? Let me go ahead and place that hole on the graph at -2, 2. Okay, so maybe I'll just change my shape slightly to make sure that it goes through that hole in the graph at -2, 2. Cool. Okay. So, got everything accounted for. Okay, let's do one more thing. Write the equation of a rational function that satisfies the given conditions. Okay. Vertical asymptote x equals -2. So that means I'd have to have a factor x plus 2 in the denominator. That'd give me a vertical asymptote at x equals -2. Hole in the graph at x equals 1. So that means I have to have a factor that cancels x minus 1 top and bottom, right? That'd give me a hole in the graph at 1. Let me look at this last one for a second first. X-intercept at 5, 0. So I'd have to have an x minus 5 in the numerator. All right, the only thing left, horizontal asymptote at y equals -4. So if I left my function as it is, I'd have a horizontal asymptote at 1, right? Because I'd have x squared over x squared. So what if I add a coefficient in there, in the numerator? What if I add a -4 in here? Okay, because then I have negative 4x squared over x squared, so indeed, my horizontal asymptote is y equals negative 4. So let me just think about everything, make sure it makes sense. And so I'd have a vertical asymptote at negative 2, a hole at 1, horizontal asymptote at negative 4, and x-intercept of 5. I think so.